For those of you who don't know the ACCU, we are a programmers group. The C, one of the C's used to stand for C and the other one used to stand for C++, but we don't like to tell people that anymore. And we publish magazines, run websites, and mailing lists. And the big event is our big conference every April. If you've not been before, it's well worth going to. 80% of people who go have been before. And I actually see Roger's got his picture on the flyer here.
It's quite scary, isn't it?
Yeah. So if you want to know more about the ACCU, there's a leaflet you can pick up about that. The other conference happening in the same time frame, which I must plug, is the BCS's SPA conference. This happens in March in Cambridge. So there's leaflets on all these down there. We have these talks every month and the subjects change, and I'm a bit embarrassed to say next month I'm going to give the talk. I'm going to give a talk on how you might go about introducing some agile practices to your organisation. Try and look at the aspects of introduction rather than what it is. We all know what agile is these days. After the meeting, we usually adjourn to one of the local pubs. I think the St Paul's Tavern seems to be the one which seems to work best at the moment. So once we finish, in about an hour's time, we'll head down the pub and you can quiz Roger more. So with that, all the announcements done, on to Roger. Roger is an outstanding member of the ACCU and a member of the ISO BSI C++ panel. So you should know what he's talking about. Here you are, Roger.
Right, well, welcome. We're going to look at the new C++ standard, and there seems to be a lot of interest in it. There have been several people who couldn't make it tonight, and we may have to do this again. So it's obviously not a language that's just sort of dead and buried. Not yet. Who knows? It may eventually. So we'll start out looking a little bit about why a new standard is needed, and then look at what's in it. And I'm trying to do it from the viewpoint of why is something in the language, what are you going to do with it, and then talk a little bit about what the language feature is. The problem with a language standard is it tends to end up talking a lot about the details, the sort of syntax, the calls you make, how things go together, and sometimes you lose, well, okay, it's a nice feature, but who on earth would ever want to use it? So hopefully I'll mention some of that. If you've got questions or comments, you can either keep them for the pub or you can wave and we can talk about them. So a bit of background first of all about C++. It's been around a while, as I'm sure you know, and Bjarne Stroustrup first put it together a long time ago now. I was not using C++ for some years. And the first standard that came out was this book called the Annotated Reference Manual. Who's read it? Yeah. How can I put this? I'm being recorded, I better be careful. I don't always find Bjarne's books the easiest ones to read. But he got together with someone else and wrote a book that was very, very good, very, very clear, very technically accurate, and was basically used by the compiler writers as the sort of reference for how the standard language was going to behave. Then world moved on a bit, and they actually got together and put together an ISO standard, which was duly published in 1998, hence C++ 98. You may have heard that phrase bandied around. And then was modified because there were bug fixes. I mean, you know what programming's like. There are bug fixes and everything, including in the standard. So a new one came out in 2003, but basically it was corrections and a few extra extensions and resolving some ambiguities. And then people worked away on the library side. The C++ standard roughly falls into two halves. You've got the kind of core language, and then you've got the libraries. And there's a kind of grey area in the middle for things like exceptions, where you've got to have a leg in each camp. And they brought out a technical report on the library with new features in that are extensions and modifications to the existing library. That was out in 2005. Microsoft did something last week. Who knows what it was? They released TR1, a beta. 2000. Well, okay.
That's pretty quick.
It's pretty good. Yeah.
3 years.
3 years.
You won't get to use it at work for the next 20.
Well, there is that. There is that. I know. Who's still on Visual Studio 6? I'm not looking. Yeah. It's a very, very good. It's got a good survival record, VC6. Whoops. So ISO standardization. This is kind of some of the boring technical stuff about how it all works. Basically, individual countries have their own panel. So here in the UK, we've got the BSI, the British Standard Institute. The Americans have got ANSI. Germans have got DIN. Various countries have got their own national bodies. And then they all kind of get together at the ISO level. And this makes things a little bit slower because you've got to get agreement at both levels and feedback going in both directions. To make things slightly easier, the Americans kind of combine the ANSI meeting with the ISO meeting. And it does get a little bit amusing because there's one point where only the ANSI members are allowed to vote and then the ISO members. So you have to make sure the right people vote at each time. And one of the, yeah?
Well, I think you were about to say it, so carry on.
Yeah, one of the UK members is actually an ANSI member as well because he represents Borland. We can talk about that later. You got something else?
There was a petition where Tom Plum voted in opposite directions.
That one, yes, 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 because you get 2 votes, you see. There are several hundred people on the ISO panel, but obviously not all of them make it to the meetings, not all of them contribute regularly. There's roughly 100, I suppose, who are active, and about half of those make it to the meetings, depending on where they are. Again, if you're a UK member, the chances are you're not going to get much financial help, so you have to kind of think about it quite hard. If you're working for a company that sends you, then it's less of a difficult decision. The one in April last year was actually in Oxford. One each year is held in America and one each year is held somewhere else. So quite a few of us were there. Who all was there at that one? Yeah. So that was a good chance for some of us to make it that don't normally. And Biana describes this process like that. A bit like democracy. It's a terrible system, but it's hard to think of a better one. Benevolent dictatorship, yeah. We can discuss that, different ways languages have of inventing standards, but that's the way we've got. I mean, the plus point is you have a lot of people who work very hard over quite a long period of time to get the sort of knots written out of the standard. So by the time the thing gets published, there's got a lot less bugs. And for a language as complicated as C++, you want that. Just for fun, the core changes to the core language, are broken down by the author. There are more names that disappear down off there. So you can see that Lawrence Crowell is at the top of the list, slightly above a certain Mr. Stroustrup, who's obviously got quite a few papers out there. Also, his name tends to get added to quite a few papers because it's quite useful to co-author with someone that actually has been around for a while. And again, for this presentation, I've put a little star next to the people that have spoken at the Accu conference, and a little triangle next to the ones who are actually members of the ACCU. I may have missed one or two, but I think that's about it. So just to get an idea of the fact that if you've been to Accu conferences, you've probably met quite a few of the people that actually design the C++ standard, the active members anyway. So why do we need a new standard? We've got one, isn't that enough for anybody? Well, things change. How many of you are using C++ every day? Okay, my hand isn't up, right? How many of you are using C#, Java, Python, Perl, Ruby? All sorts of PHP, HTML, JavaScript, all sorts of stuff. I mean, there's a lot of languages out there. They've got strengths and weaknesses. What's the right tool for the job? Depends what the job is. A language you know well is probably a good tool for the job, but you might not want to do some things in some languages. But the flip side of that is that some of the newer languages that have come out have got things that actually be quite nice to have in C++. And they've been field tested, and they've had a couple of iterations, and they're fairly solid. One of the interesting things about C# and Java, of course, is they started out, both of them, as very, very simple languages. I used to teach the Java for non-C programmers course for QA, for Java. And in 4 or 5 days, you basically did everything in the language. I mean, there were more libraries you hadn't covered, but 5 days, that was it. You said, there's no more language to cover. You can't do that now, because the language has got more complicated. And C# is getting really quite fun. It's nearly as hard to read C# code as it is C++ if you're careful. The other reason for changing the language is that C++ has got some rough edges. I'm sure you can all think of some. Perhaps rather too many. In fact, some people think of so many that they decide to give up completely and go and write VB. Or perhaps not quite as far as that. Unfortunately, it's quite hard to change a language because there's code out there that already exists. But some things can be done. And some of the rough edges can be kind of honed down a bit. It's one of the things where C++ is both its greatest strength and its greatest weakness. If it wasn't based on C, it probably wouldn't have become as popular. But it's based on C. What can you do? The other major change is, as Herb said at the Accu conference recently, the world is going parallel. How many of you have got a dual core box on your desktop? Okay. How many of you can write reliable code in the existing C++ standard that you can guarantee will work on a multi-core machine? Yeah, you're wrong, isn't it? You know, the language itself needs changing, and some of the libraries need changing to support that and to put the magic words in to make sure that we know what it's going to do when you run it on a multi-processor box. But changes have to go in line with the language. It'd be no use trying to sort of fit Python into C++. You end up with saying it was neither one thing nor the other. There might be some things you can take on board, but you've still got to stay with C++. So what is in the kind of spirit of C++? What's something that's good for going with the C++ language? Well, one of the things that people are very strong on is it's multi-paradigm. A bit like the old Perl, there's more than one way to do it. I found it a bit odd going from C++ and when I started learning Java and C#, because you force back into a kind of object world where everything's based on a class and everything's sort of single hierarchy. C++, well, you can write that code if you want, but you can also write other code, procedural code. You can have multiple inheritance. You can write template metaprogramming and live to tell the tale. And we don't want to restrict that. So some of the proposals that were made, people said, well, yeah, but you know, that would make it harder for the more than one way to do things. Trust the programmer. It might be very, very foolish advice, but that is there in the spirit of C and C++, that you should be allowed to do things. It's up to you to decide whether they're good things to do, or perhaps the person reviewing your code, but you should be allowed to do them. Another very important one is if you don't use it, there's no cost. Now, that's not always completely possible. Exceptions are a good example. In theory, if you don't use exceptions, then it shouldn't matter that the language supports them. In practice, some implementations do have a slight overhead. RTTI is another example where the fact it's in the runtime can make a small difference. But in general, there's a very, very strong resistance to having anything in the language that costs you if you don't use it. And that actually makes some things very difficult to do. And this is a good one as well. Don't break anything that works. So the theory is you can take your 3 million line program and throw a new compiler at it, and it will still compile, which is good. Because if it doesn't, you've got a nightmare. And the other thing that's very important about C++, and one of the things I like most about it, is basically, if you can possibly check it at compile time, then do so. It's much better to have a compile time check than a runtime check. Okay? Why? Anyone like to answer the question?
Still there at compile time.
Still there at compile time? Yep. That's right.
There's a good chance you'll be there at compile time. Depending on what you're doing, there's an excellent chance you won't be there at runtime.
That's right. And runtime might happen out there.
When that tried to take off.
That's right.
I don't think it was really
Yeah.
though.
If you can check it at compile time, then the compiler is reading every line of code and checking every line of code. At runtime, you may not go to that line of code until 3 years' time, and suddenly you discover you had a bug, or someone else discovers that the guy who left 2 years before had a bug. And that's one of the things, again, I find, in general, I'm very much in favour with the C++. If you're using a language, say, without strong typing, it's very, very easy to write complete garbage. And there's no compile stage, so of course it compiles, because there's no meaning to that phrase. It just doesn't work, which is not always what you want. Biana has some principles for the new standard, and the last time I did this, no one could read the URL, so I cunningly changed the colour. Oh well, best laid plans. And he said that his view, the key principles for the new standard should be no major changes to the language, as much as possible done through the library, because language changes are very expensive, library changes are much easier to do. And the idea is to make C++ a better platform for a couple of key things. First of all, system programming, where it's obviously very, very useful and important and still used very widely, and also easier for people to get started. because it's quite hard. The learning curve is very steep, and until you're fairly experienced, you can do quite bad damage very quickly. So what actually did we get? Well, we have got major language changes, lots of them. Nearly all of them are extensions to the core language, i.e. what you've got now will just work, but there's more things you could have done if you were using the new features. Unfortunately, it does affect the ABI application, the binary interface. So if you've got a program compiled with an old compiler and with a new compiler, they ain't going to work together. You're going to have to compile the whole lot, almost certainly.
Given the amount of template code in the library, changing the library changes the ABI as well.
Yes. If you start sharing C++ templates, particularly between, say, in the Unix world, an XE and a shareable library, or in the Windows world with the DLL, yeah, your bets are off. They should all be with the same version. Sadly, no one seems to realize this, because you can still run the thing, it just doesn't execute correctly. It'd be very easy to put the magic hooks in to say, sorry, these versions don't match up. There are some minor language changes as well to smooth out edges, and we might cover some of those. And there are quite a lot of new library components. Many of the library components are in this TR1 that Microsoft has just released a version of. And handily, there's a book, there's probably more than one book, by Pete Becker, talking about the extensions. And nearly everything in TR1 has been adopted in the new standard. So here's a list of what I picked out and decided were the key changes. The first one is, well, it depends if you're a kind of language lawyer or a user, what you call it. R-value references. Okay, I'm happy for you. Move semantics. Oh, that makes a bit more sense. I've got an object and I want to copy it here, but I want to get rid of the original. Well, I want to just move it. Why? Because it's an awful lot cheaper than allocating in a lot of memory, copying stuff across. So the driving force behind it is the move, but the magic syntax for it is this thing called an R-value reference. And that's one of the things I found with the developing standard is you have to keep your eye open to see what the motivation is sometimes, because otherwise you've got no idea why this new syntax is appearing in the first place. So we'll go through some of these and see what they actually look like. So the idea behind this one, the key motivation, is to get rid of unnecessary copying by finding a way of moving data around. Now there are tricks you can use in the existing C++ 2003 to do some of this, but they're kind of horrible stuff you don't really want to think about too much, and they don't do a complete job. So the solution was cunning and devious, I must admit, and in theory this thing should work. How about that? 2 ampersands. So you've got a reference with a single ampersand, and now you've got this type with 2 ampersands, an R-value reference. And what you do is you create an overload. 2 functions, and the signature differs because one of them takes a single ampersand and one of them takes 2 ampersands. That's the sort of language side. And what happens is the compiler decides which one you can call based on whether you can bind the variable you've given it as a L value or an R value. And the right things happen basically under the covers so that you end up where temporary objects go to one overload and everything else goes to the other. So when you're implementing that one, you know you've basically been given a temporary. So you can destroy its internals because no one cares. So you can just swap the contents into the object you're assigning it to, for example. Of course, you'll realize that that relies on the fact that you have actually got the right overload set. If you just write that one, and you don't write the one with a single ampersand, you've only got one function, so it will be called with temporary or non-temporary objects. So it's not a sort of simple thing to write correctly, necessarily. But the good news is, it's very easy to use, because here I am using it. How can you tell? Well, you can't. In the existing standard, what happens with that is I come in with 2 const references to strings, tag and contents, and I'm generating a slew of temporary strings. And there's not really much that the compiler can do to avoid generating 1, 2, 3, 4, 5, 6 probably temporary strings and getting rid of them again. Which is a bit pointless really when you think about it. But with the R-value reference overload, the compiler can generate a temporary and then just effectively move all the additional data in. So it generates one temporary object and basically appends to it, and then the temporary just gets assigned straight into the string and then returned out again. Howard Hinnett did some testing on a sort of STL algorithm doing some sorting and moving a few collections around, and he got a performance increase of 187 seconds down to 13.6, because basically the allocations and the copies disappeared. And what's quite interesting is that's actually probably, in that kind of example, better than the performance benefit you get out of using a garbage collected language. The reason being, you're not generating any garbage. So there's nothing to collect. It's just better. And that, I think, is going to be, from the performance point of view, quite a significant thing for the standard. How many of you currently think about the signature of functions and perhaps pass in a reference to a non-const object to get data back out, rather than getting a copy out of a function? Yep. And now we might not need to, depending on what you're actually doing. You can actually just treat it more the way you would intuitively, make it clearer that you're returning something, and under the covers, things will be moved, not copied. Now, obviously, we're going to try and do as much as we can to the existing components in the standard. If you've got 3,000 collection classes you've written in-house, then the same sort of work will need to be done to them to put in the extra overload. Any questions on that one?
So the overload along with string, is that right?
Yeah, yeah. Which is why it's a very, very nice change, because you just change the header file and the implementation, and you just compile your code and it works faster.
So something that you can effectively say, you've got 3,000 collection classes that need to be changed, you can do it incrementally.
Yeah.
Over time.
Yeah.
Particularly most.
So it's not a kind of viral-like one. It's not like adding const, which was, once you added it to one class, it just kind of ripples everywhere. Next one that I think is quite nice is the whole area of working out what you're talking about. Decal type, auto. You're doing some manipulations with iterators on a standard vector of standard strings. So you end up writing stud vector, stud string, colon, colon, const iterator. Somehow I've lost the will to live. Now, I know what I'm doing, and I'm going to call collection.begin. And the compiler knows what the type is, because if I get it wrong, it gives me a compiler error. Well, I can just use the word, I will be able to use the word auto. And auto says to the compiler, loosely put, okay, you know what the type is. Get me one of them.
It's BB in C++.
Yeah, but it's not. And the reason it's not is it is actually a compile time, and that's the thing. That's, again, one of the, going back to the spirit of C++. It's a bit like auto in VB or other languages, but it's not, because it is actually a compile time different type. It has a type. It's just you can't be bothered to write it out. So some examples of that and decal type down here, we can say I've got a vector of something. Whatever the declared type of I is, it's a vector of that. Which means if I change that, that changes automatically. And here, auto beg equals vec.begin. I don't care what type it is. And I think that's really rather nice.
Well, that's RTTI compatible with it.
Yeah, it's still got a type.
Yeah.
Effectively, the compiler under the covers just goes off and fills in whatever the type really is. And you can also, if you wanted to, you can then do a decal type on beg, because it does have a type. It's just...
I could just see this leading to bad coding practices, perhaps. I don't know.
It may do. We'll have to see when people start abusing it.
And what everything could lead to that.
The other place it comes in is with return values. If you're writing templates, and particularly the return type of a template function depends upon the type of the arguments, currently you're a bit hosed, really, because you ain't going to fly. Whereas what you can do is a bit of magic here, where at the end here you put the decal type. There are syntactical reasons why it has to be this way around. The auto is basically just a placeholder that says, I'm not telling you what the return type is, you're going to have to wait. And then I've got the arrow, and then the return type of this is the return type of whatever t plus u is. That one I think is going to be probably less relevant for most programmers, because most of it will be in library code, I suspect. But I can see that making code a lot simpler. Yes?
Sorry, does it not also have the problem that if you're reading someone else's code, there's a chance
Yes.
Does it really matter?
Does it matter though?
Does it matter? I mean,
Yeah.
there's acres of dynamic code out there that you can make rat's ass
Yeah. Yeah.
perfectly well. And when you see bazillions of type defs to get around that, and you just end up losing
Yeah.
the will to live.
Yeah.
And wonderful hash defines as well, and joys of that.
Yeah, and as I said here, the other solution was type traits, and they're quite a pain.
It'll save gigabytes of hard drive space alone. And version control systems, you know, imagine the amount of space
Yeah.
saved with that. The amount of money this will save you.
David? Next.
I was going to ask why instead of auto you can't just have decal type? Why do you have to have this funny single pointers?
It's to do with parsing rules, and people who know much more than I do about writing compilers said it can't be done. So
It probably needs to have
yeah, there's all sorts of stuff.
It's how you identify T and U.
Yeah.
T and U have not been identified at that point in the past.
what happening.
T and U.
Parameters in the things in the
Yeah.
expression. You do decal.
You may not be able to actually, at the point where the auto is, you may not actually know everything you need to know.
It is in that example.
In this example, it is. Yeah. Yeah. We can talk about that one further in the pub.
Oh yeah, you haven't instantiated.
No. If you put decal type where the auto is,
Yeah.
and the compiler goes truncheling along, it reads capital T, reads capital U, reads lowercase t, doesn't know what the type
Yeah.
is.
What T and U?
Yeah.
Little t is the one.
Little t over here. That variable little t. So and there's other reasons as well. Also, they tell me. Variadic templates. Again, this is quite nice. If you're writing templates that take variable numbers of arguments, it's a right pain because you've got to write one and then another and then another. And at some point you run out of steam, or your compiler runs out of grunt, and you stop at 8, perhaps. And then there's bound to be someone that needs 10 parameters, isn't there? And quite a lot of the Boost template libraries have got this problem, or feature. I should just use the approved word. That they specify somewhere how many times this thing's instantiated, and once you hit the limit, you've got to make some changes. All the variadic templates does is say, well, let's just put ... We know about ... It means just keep going, and a bit of magic so you can actually access what that type is, and then you can pass it down recursively or whatever. So things like the type lists. Who's read modern C++ design? And yeah, the type lists in that. This kind of thing might be useful, very useful, that sort of idea as well. And on the flip side, it also makes compilation times less, because rather than having to cope with, I don't know, 50 template instantiations and the compiler working out which one you meant this time, it's only got one. So it's quicker to find and less symbol space is used. So for example, down here, we've got these 3 little dots that are cunningly in purple so you can't read them. And it's a struct called a tuple. And all we're saying here is that there will be a struct called a tuple. We may not have given any, but the compiler now knows that that thing exists, and it takes a variable number of arguments. And so we then instantiate one here, takes an int and a float. And obviously somewhere we'll have got the implementation of that, which I'm not showing for now. Again, I'm not sure how much difference that's going to make to most programmers, because not that many people write the things that use variable number of arguments for templates. But we'll all benefit from the fact that those things are now faster.
Make a big difference to Andre.
Indeed. Have to write another book or something. Yeah. New for loop syntax. Now I like this one as well. Who uses the new for loop syntax in C# or Java? Anyone? Yeah. For loops are great because you can cause so many bugs so easily. Just iterate incorrectly, off by 1 errors, changing the for loop variable when you're halfway through the loop, and suddenly we had a good example a couple of weeks ago somewhere I'm working where someone was trying to delete some objects in a collection, so they did this classic delete n and then add 1 and delete n, and so they're deleting every other one, but they hadn't realized. So what they've done is to put in this new idea where you can just use the colon. Hey, it's C++, who needs a word? It looks a bit like the Java one. And you just say for, again, cunning use of auto here from before. X is a reference to whatever's in there. Wherever it is, double it. That's great, isn't it? A lot shorter than writing that code now in C++ 03. Alan?
You stick to the new initialization syntax as well.
Yeah, I know. That's also something else you can do now. You can actually do that and it will compile and do what you'd expect.
Wow.
Oh, I got it wrong. That should be the major language feature. However, we don't like magic. Cunning as it might be and everything like that, we don't really want it just to happen out of the box. So you have to include a header file. Iterate a concept. It's actually coming out of some of the concepts work that we'll briefly mention. There's been some debate about whether it should work by magic without needing to include a header file, which I think is a bit rich coming from a language where the archetypal program starts #include stdio.h printf hello world. You know, we're used to including header files. And the advantage of doing a header file way is it's open. You can do extra things to it if you need to. It's not something that only the compiler writer can do. It's not tied to specific details that you can't change about the way it works.
But in a sense, you're not just including a file in that case, are you?
You're including enough so that basically what you're doing in here is you're telling the compiler what concept that collection uses to give you the things you need to do the for loop.
Right, okay, so you're not switching on sort of mode of the compiler, you are
No.
providing...
You're providing magic for the compiler, but you can write your own code to do the same thing for your own collection classes. So you can do it differently. I think it does, because again, it may be a different header file, but the idea being you'll provide a concept map for array, and it will know how to do that as well. That was the idea. So the language will arrive out of the box with the right magic for all the predefined library types and native types. But then you can add your own if you've got some particular requirement. Initialization, as Alan noticed, I've done that in the previous slide already. Initialization in C++ is a pain, because it's got sort of leg in each camp. Is it like C, or is it like C++? And sometimes the joins show. So one of the ones where I was quite surprised to discover is currently you can't write that, because the language says that for a for loop variable, you must initialize that with an equals. Why? Well, history. So various people have written various papers to try and rationalize it without breaking too much. And it's getting pretty close to final wording on that. And the end result should be, basically the language just behaves a bit more elegantly, and you can just write initialization the way you expect, and it will do the right thing. Currently, it's a right pain if you want to do something like this, set up a vector of strings with 4 strings in. You can't just write that, sadly, which is one of the reasons why some people resist using standard vector, because it's so difficult to initialize a vector thing. They stick with arrays of pointers, and that's much more difficult to get right. Well, I find it is anyway. Your mileage may vary. Concepts. Okay, I don't pretend to understand concepts, but they sound like a really good idea. The basic principle is simple. You've got things like standard set. Who's used standard set? Yeah. Standard set of T. What does T have to do, that type T? A list of things. It's probably got to be default constructible. Where's my standard? If I get it wrong, what happens? I get some horrible compiler error in some header file I didn't even know I'd included. If I'm lucky, I get a sort of stack walkback of the compiler that eventually I find a line with my code in, but it doesn't often tell me anything meaningful about what I've done wrong. The idea behind concepts is you can express in code, so I can understand it and so can the compiler, that this particular type must be able to be comparable, be constructible, etc. If it doesn't work, I get a compile time error that makes sense. I suspect strongly that a few brave people will write these things, and most of us will just use them, and it will make our life easier as programmers. And again, some of this you can sort of fake in the current version of C++ by doing nasty tricks like trying to instantiate a class where there's a Boolean parameter and one of the instantiations will be successful, another one won't, and you make the Boolean depend upon some horrible template magic that only works if you've got an overload. You know the sort of thing, you might have seen it and blenched horribly. It should be a lot clearer to understand what's going on with concepts. That's proved quite a difficult one to nail down. One of the reasons it's proved difficult is because C++ is probably about the first language to do something like this in quite the way it's doing it. So there's not that much existing practice to work from. There is some with the whole design by contract, but it's not quite the same thing. Then the threads and memory model. How many of you are writing multi-threaded programs in C++? Yeah. Do they work? They seem to, don't they? Most of the time. The problem is that it works great, and you've got one CPU on your desktop, and then you put a second one in, you get 2 cores, and then you get 4, and Intel have got these plans for I don't know how many cores in about 5 years' time. It's all going to end in tiers because it gets a bit more complicated. And the C++ standard doesn't define how this thing works. The memory model is very, very simple, the model of execution, and it's pretty kind of abstract. It doesn't really have anything in it currently to deal with what's it mean to have a race condition. There's no mention of that. Threads aren't mentioned in the standard. So how can you define a race condition when you don't even know what a thread is? So there's been a lot of work at the core language level to try and come up with a really rigorous definition of what memory accesses do and when 2 threads can see the action of each other or a third thread. And I know a lot more now than I ever did before about some of those wacky bits of hardware out there, particularly the IBM guys. They seem to have got some really scary stuff going on. So you can do things where a thread writes something and writes something else, and 2 other threads running and other processes can see those writes in different orders. Or arbitrary order.
Is that because of the way the memory is written?
Yeah, it's the way the memory and the caching works. In the desktop Intel world, currently, in the 32-bit world, we're nicely cushioned because the SMP architecture is believed to make a lot of constraints, although no one's exactly sure because it's quite complicated getting this right, I believe. But in theory, you don't get those sort of problems. But the 64-bit world, they've released a lot of the constraints. Now, the reason is for performance. Because if I do a write and I've got to make sure all the other cores on the box have got the data, then I might as well have a single CPU box.
The ultimate reason is that the MESI model that they use for implementing cache coherency protocols doesn't scale. The old Intel processors, they only scale to about 4-way. And you've got
You can't do that.
You've got the 16-way Unisys boxes. They used a different directory structure on it. They didn't use the SMP architecture.
Yeah.
Then what happened is AMD came along and said, hey, let's make performance supercomputers, get rid of this and do something called NUMA.
Yeah, there's all sorts of reasons for performance and the way the memory access goes. So there's good driving forces behind it, but the problem is the language itself didn't, now it does, didn't support a way of describing what was going on in a way you could actually reason about it and say, this program is provably correct and it will work on any architecture supporting C++. And I won't suddenly find it stops working. And the problem with the sort of bugs you get with this is debugging them.
Is the C++ standard going to come with an abstract machine model?
It's going to come with some,
and execute?
not exactly, no, not unless you want to write one.
Because, I mean,
That would be quite nice, wouldn't it?
Ultimately, in order to create a program that's guaranteed to work, that's what you're going to need. You're going to need a fully defined abstract machine model.
No, it's not an abstract machine. That's the thing. It's unlike Java and C#, where you've got a VM and you can define what volatile means in C#. And it's up to the individual people to make sure that their implementation does that. C++ doesn't want to force that on people. So it's trying to make, it's a bit of a tightrope between let's make it really, really consistent, and then it's kind of hard for some hardware people to do it, but that's just tough. Or let's make it really open-ended as it is now, and different hardware people can make different decisions. Different compiler writers on the same hardware can make different decisions about how you do things, and that leads to mayhem. So they're trying to form a little line in the middle, and there's a bit of a sort of, I think it's fair to say, a bit of a division between what you might call the Microsoft side of things, or the Intel desktop side of things, and the kind of Linux, hardcore IBM people who see things very differently. I might mention that in a little bit when we get there. As well as the compiler support, we need a little bit of low-level support for threads. And again, at this stage, it looks like it's going to be the minimum you can get away with, so you can then build things on top, knowing that the bottom level is there. And maybe at some later point, TR2 for the library will come with some more interesting things you can do with threads. And partly to do that, again, we've got atomic variables, where access to these is special, and certain guarantees are made that if you write to an atomic, it either works or doesn't, effectively. You don't have any possibility of seeing a partial value. And there's also guarantees made about when you access an atomic in another thread, what you'll see and what you won't see. The reason for that is that if you use a classic lock, mutex lock or something like that, it's quite painful, doesn't scale. It's a lot faster if you use some sort of atomic where you're not doing a kernel transition. You're just doing something in memory. However, it's also very difficult to get to go work right. It's quite nice to write these lock-free algorithms, and 99.997% of the time it works, and that 0.003 it comes up with the wrong answer. And again, if you get a new algorithm, it tends to be some sort of publishable result. But that's fine, because if it's published, you can then use it. So an example here, using some of the new stuff. The exact words here is not yet finally decided, but the idea is you've got an event counter here, and we're saying it's a special thing. It's an atomic ulong. So it's of size unsigned long, but the right magic happens under the covers by the compiler writer to make sure it does the right thing on this platform. It might have to be aligned differently. It may even, in some environments, have to be in a different part of memory. I don't care. Do whatever you need to do. It's possible I might be on an environment without them, in which case it may end up being emulated. So that's something to watch out for. And then when you increment it, I want to add 1. Special fetch add, and memory order relaxed. What's that saying? Well, I don't actually care whether all the other CPUs on the box see the 1 added now or a little bit later. It's the stats counter. Hey, give me a break. If you read me a millisecond earlier, I wouldn't have done this update anyway, so I'm not too fussed. And similarly, when you actually get the value, again, do a load, but do a relaxed memory order. So that will be on certain hardware platforms significantly faster than doing effectively a synchronous read. On an SMP box, it doesn't make any difference what you put there, because they all do the same thing pretty well. Yes. Yeah, and the atomic bit basically does that guarantee. It says, if you do 17 calls to inc, then you will see the right values. If you always add 2, you'll only ever see even values. And those are the guarantees. But when you'll see them is the bit that's specified by the memory ordering. Part of the problem is there's 2, well, there's more than 2, but there's 2 that we've whittled it down to, ways of looking at memory ordering. One is what's called sequential consistency, which kind of means that if you took a kind of step back at the hardware, you could kind of put together an order in which everything happens, a global order. Which is really nice, and it's how most of us think, but it isn't the way the hardware does it. It's a bit like relativity. That happens before in relativity. Well, you can do it if they're far enough away in space-time, but if they're too close together, it depends where you're standing, whether it happened before or after. So there is no global ordering, and it's a bit the same with computers, not for the same reason. Or this thing called weak C4, which is causally consistent cache coherent or something. I can never remember what it actually stands for. James probably knows.
Is that often termed as programming consistency?
No, it's called C4. Everyone always calls it C4 because it's the 4 Cs. Basically what it's saying there is it's just making 2 guarantees. One is that if A happens before B in the same thread, then if I go in the same thread and read back, I'm going to get things in the same order, and other people should see things in the same order. So 2 threads, if A and B are updated, the other thread will see them in a consistent order. And then the cache coherency is basically making guarantees that you end up with a consistent. You can make the cache consistent. What that actually means is a bit vague. And then
That sounds like the classic definition of programming consistency.
it may be, yeah. And again, part of that is coming out of the sort of networking model, where you've got like the old day of Occam and that sort of stuff. Yeah. And again, there's a bit of a debate about which of those, and the expectation is that probably the default behavior will be sequential consistency. So all the PC guys can just say, oh, that's fine, I'll use that. And then the people that really want to get the performance out on the sort of, the multi-core Linux world can, for certain cases where it's important, can drop that back to weak C4. And it is believed, again, no one's actually managed to prove it, it's believed that you can write your algorithm using sequential consistency, and then you can change to use weak C4 in 1 or 2 places, and if you're careful, it will still continue to work.
Is that related to bisimulation?
I don't know, I'm afraid.
I believe there's actually proofs of that.
Some of it
To
is,
do with list-based scheduling.
some of it is provable, but I'm not sure whether it all is. that discussion I tended to kind of keep a fairly low profile because a lot of it was people who are doing stuff that I don't know much about. Lambda. We may get this. It's kind of close to the wire. It may not come in. The basic idea behind Lambda is code is an object, right? Code and data is the same thing. So why can't I just write a few lines of code and have that become a method in an object? Ideally, transparently. Quite nice. It works in some languages very, very easily, and this is where we get bitten by one of the problems of C++, is that in C++ we've got a much less abstract architecture. We are in charge of memory. So I've got this thing there, and it's talking about, in this case, factor and n. They're variables and sum. Am I talking about a copy or a reference? Well, depends, doesn't it? If I talk about a copy, then I can add as much as I like to sum, but it won't affect that one. If I talk about a reference, well, that's kind of cool, but then supposing I want to pass that off to an asynchronous thread for execution, my object now disappears. So you're kind of damned if you do, damned if you don't. Which do I want? Well, I don't know. So, of course, being C++, you get both. So that little ampersand there means, by default, pass things by reference. The syntax may change a little bit, possibly. And there's again a question, if you don't want the default, what do you put? Do you leave nothing in there? Or do you put in a question mark? This is kind of keyword design without using the alphabet. It's quite fun, really. But, yeah, it's strange. I suspect it's going to be a little bit tricky to get started with that, and some of the code may end up totally unreadable, but that's nothing new in C++. But with care, it can actually generate some really useful stuff. I mean, this is a good example. For each is great. Who uses for each? Yeah, it's magic. The only problem with for each, the first two parameters are great, but it's the third one that gets you, isn't it?
That's why I don't use for each.
That's what, yeah, that's right. And people say, well, you can use this magic boost lambda. I believe you can use it correctly. Yep. And if or else you can write an extra function, and then you're breaking your encapsulation. So this will make it a lot more possible to use for each, and a lot easier to use it. Garbage collection. This is quite an exciting one as well. We lost a complete day on the Oxford meeting to discussing garbage collection. Is it good or is it bad? Wrong question. Yes, yes. Poe, I think, is the answer. C++, we know and love, has got what they call deterministic finalization. That's the general word. Destructors. When do destructors fire? You know exactly when. Your object gets destroyed at the end of the scope, and the destructor gets called. And if you haven't get the destructor called, you've got a compiler bug, and you can get it fixed if you're lucky. So you know when it's going to happen. That's how you manage your memory in the C++ world. And when that works, it's great. Unfortunately, there's a couple of problems with that. The first is, sometimes you're not quite sure whether you can actually destroy the object, because has everyone finished looking at it or not? If you've got some complicated data structure that's got cycles in it, how do I delete that? Well, I'll delete the first one, and the reference count goes to 0, but it won't go to 0 because there's a link that you didn't know about going right round 47 objects back to the beginning again. And the second problem with deleting the object now is I'm running on a 47 core machine, and I delete one object, and it's got to put the memory back in the memory pool, which of course typically means doing some sort of lock to access memory, which is a bit of a hit on the performance. And it can be significantly faster not to delete the memory at that point, but to have it collected later on by a garbage collector that can run as some background thread. And for those reasons, and also the case where you just kind of forget to delete the memory, which is also quite common. Who's ever been bitten by that? Yeah, okay. We're among friends. It was felt good to do the magic necessary to the language of C++ to support garbage collection. Again, not that you'd have to have it, not that it would be mandatory. An implementation might not support it, but the language would support the necessary keywords so you could make something that worked well with the garbage collector. A couple of things that are necessary. Most of the garbage collectors work on, you basically scan through memory looking for pointers. You've allocated address 1, 2, 3, 4, 5, 6, and there ain't no 1, 2, 3, 4, 5, 6 anywhere in your process address space, it's not in use, so you can reclaim the memory.
Maybe.
Maybe. It's the maybe that we want to try and solve. So you can specify to the compiler, this pointer I do some cunning tricks with, like put a status bit in it or XOR it, because you can get a quite cunning data structure. Two-way lists using a single pointer saves a lot of memory if you've got lots of nodes with small payloads by XORing the back and forth. But of course that means all the pointers disappear, so your garbage collector just throws the whole list away, which is not what you want. And the other problem is you're doing graphic manipulation and you've got an 8 meg image here and a 16 image there and another one there. You've only actually got 6 pointers in your machine, and your garbage collector is scanning through all these GIFs and JPEGs, finding pointers all over the place. It'd be quite nice to be able to tell, again, the compiler, the runtime, that this bit of memory doesn't contain anything interesting. Well, it's interesting to me, but not to you. And that bit will probably go in. The problem really with C++ and garbage is litter collection, which is a word we kind of, I think we coined in the discussions. Litter collection is, I've got a small little leak. I forgot to do one delete, and I've got 17 objects allocated and 16 freed, and that's quite nice if something will go and fray away the memory, please. Full-on garbage collection is different, where you don't take any responsibility for your objects at all. Magic happens, and they just get tidied up. Who's used languages like that? Yeah. And how does it work?
For what?
For what? Yeah. Again, that's part of the problem. It's, again, multi-paradigm. It works really well for some things, not for others. The real killer is the resource management. Garbage collection relies on the fact that any particular byte of memory looks much the same as any other particular byte of memory, and it's all interchangeable, so you're just going to claim it back. It doesn't really matter too much when you get it back. Okay, it's not true in all environments, but that's the basic kind of mindset. Bit different when what you've leaked is a file handle or perhaps a database connection. And so you've got a license for 8 connections on your database, and 7 of them have just been leaked and will be picked up by the garbage collector next Tuesday. In the meantime, you've got a life to live and you can't get on the database. So in the C++ world, you normally use destructors to manage that sort of stuff, and that will continue to work. In the non-C++ world, the Java, C# world, you end up having to write a lot of code anyway normally to do that kind of resource management. Well, actually, no, you don't. What you do is you start out not writing that sort of code, and then you get problems, and then you realize you're going to have to write it anyway. So I think it was a Microsoft research paper that they reckoned that nearly all finalizers, .NET finalizers in the real world, are broken, because it's extremely hard to write them correctly. How many of you have ever used a .NET finalizer and seen them littered up in the code? Yeah, it's kind of worrying, really. So the jury's still out on that one, and what we'll actually end up with in the standard is a little bit unclear at this point. There will be something in there to support the necessary hooks, and it will certainly provide the hooks for litter collection. We're not at all keen on trying to do any other sort of resource management. So if your destructor does something, like closes a file, then if you leak it, tough, that file just won't get closed. Okay, 5 to 8. Minor language changes. These may, of course, a bit like the aha moment from Alan, these may be more major than I thought. A list of things that I'll go through very quickly unless you've got any particular interest, in which case wave. Enums are a kind of half-baked concept, as Stroustrup says. They're right pain, actually, aren't they? You define an enum and the name leaks outside of the enum, and you can more or less indeterminately treat an enum and an int as the same thing, and it kind of half the time just converts back and forth. You can't specialize templates. Yeah, there's all sorts of stuff. Something that was first introduced for C++ CLI, which is the version of C++ that Microsoft put onto their .NET framework, is enum class. Now that's a different beast. In the C++ CLI world, it maps down to a .NET enum class. In the non-Microsoft world, when you've got the new compiler, it will still not map down something different, and the differences are that you've got no conversion to int, and also those names don't leak out. So it's what enums sort of should have been, really.
Use them for template specialization.
I believe you can, because they're genuine first-class objects. I haven't checked the details of that, but it should work. Const expression. One of the nasty things about C++ is that not everything that you actually can work out yourself in your head looking at the source code, the compiler can't always do the same thing. So if you're trying to declare a constant, constant, for goodness sake, the compiler can work it out. So you write a little expression to work it out, and for some reason the compiler decides it can't do it at compile time, it has to do it at runtime. So you work out the value and type it into the code. Anyone done that ever? Yeah, I've done that. There's all sorts of problems with functions that run when the program's loaded, particularly if you're thinking it's going to be a constant, because there are certain things that you have to actually have genuine constants for, like templates and stuff like that. And you've got issues with, if you've got a multi-threaded program running, who got there first, that sort of stuff. So one of the very small but probably reasonably significant changes is that if you decorate your function with const expr, and it does certain things inside it, if that's a constant, then so's the result at compile time. If you don't decorate it, it isn't. But if you do, it is. And therefore, the compiler can actually generate, in this case, a rather silly case, an array whose size is the absolute value of the difference between m and n. It's fitted on the slide, but you can see the principle. You can't write that currently because abs is just a function call. So you end up using a macro, or worse. Yeah?
I presume that things that can't be computed with concept that compile time will produce some kind of error warning.
Well, exactly the same as currently. If you tried doing that currently, if I did it in the OX world with a function that didn't have const expr, I'd get exactly the same error as I currently get.
When you compile the function abs and you do something inside the definition that doesn't allow it, then it will get an error.
Yeah. If you, for example, in here, if you then called another function bill that wasn't decorated, it wouldn't compile. Which is one of the reasons for having the word in. It makes the job of the compiler writer easier because he knows whether you're trying to compile a function that is const expr or not, and therefore can do the checks.
I presume things like float won't work in there.
That should work. Yeah.
Ooh,
Yep.
IEEE compliant
Be nice.
implementation in the compiler.
So are the expressions going to be evaluated on the hardware the compiler's running on, or as on the hardware the compiler is targeting?
Yeah, that's going to be fun, isn't it? If you're doing cross-compilation, what do you get?
What happens if I have faster?
Yeah. Those are questions I can't answer offhand. I'm sure it's documented somewhere. You probably get what you pay for. It's probably, yeah. Static assert, again, another small one. There are things you can actually check at compile time, but how do you tell the poor punter that it's gone wrong? And all static assert says is, here's the condition, and if it ain't true, in some magic way, as yet unspecified, because it's up to the implementation, do something with that string. So a sensible compiler will obviously generate a diagnostic with error at line, whatever, and then that text in it. But as always, we're a bit vague about what actually must happen, but that is the end result. And that's very useful, particularly useful because this can also work inside a template. So you can generate a compilation error if you've got some constraint that you need that's not satisfied by the particular instantiation values. Some of this magic is currently done with template metaprogramming in Boost. And A, it's quite difficult, and B, it's quite costly. This should be a lot simpler. C99 is a kind of funny thing because it almost happened. And there are some compilers that have bits of it in. They're kind of cherry-picked. And we've done the same again, you see. Some of the things that are in C99, the C++ panel has gone for as well, which makes sense, like long. Well, that almost makes sense. More details if you're interested. Unicode characters again. So we've now got, in the new standard, new types, char16t, char32t, and new literals, U and capital U, or either strings or characters, which is quite fun. Again, there's some debate about generalizing that, which may happen. And there's also the interesting difference that in C99 world, effectively those are type defs for an underlying unspecified type, depending on which compiler you're running. In the C++ world, they are actually separate types, so you can overload on them, which is the real reason for doing it. They are going to be reserved words, I think.
No, I mean the literals. You couldn't use those for the variable.
No, that is a literal. It's you.
Because that'd be quite interesting, because you could then start writing your C++ in Chinese or something.
Yeah. You can do some of it. There is a list of the Unicode character set, but that isn't the way you do it. Delegating and inheriting constructors. If you're doing inheritance for various reasons, sometimes you want to just have all the behavior of the superclass and make one minor modification to a method. And you have to write 47 constructors because they're the ones you got from the parent class. And even worse, you write 3 or 4 constructors and they're all basically doing the same thing, but it's not that easy to chain them together. And again, hopefully both of those are going to be fixed so that you can share constructors. One can chain to another, and also, as in this case, you can implicitly pull in the constructors from the class you're extending, which just make life simpler. Right angle brackets. Yay, finally! If you write that with 2 right angle brackets and no space, it gets an error. You have to put a space in. Somewhat unexpectedly for me anyway, it was actually quite hard to change. David, obviously it would be David, he's good at that sort of thing, came up with some code that compiled correctly with the space in and the space removed, but meant different things. Yeah, if you think about it too long, you'll probably go mad. That's not an issue in C# Java, because their generics don't let you have non-type template parameters. But C++ does. So what you can put in as a template parameter is you could have one right shifted by some value. Yeah, I mean, you could argue whether that's good or bad behavior, but you could do it. And if you did do that and someone decided that actually they ought to treat that as if it were the end of the template, you could get a bit upset. But in the end, they decided, well, just tough. Deal with it.
There's one person in the whole world who should come up with the problem. He can't have been around for that long, and I'm sure there's enough effort to make sure he's not around.
And I suspect there will be very, very few cases that actually do break. It was quite contrived. But that obviously is a concern. You know, you don't want to have a transparent breaking change on code when you use a new compiler. But that is quite nice, because it has always been a very embarrassing thing to have to explain to people why it doesn't. Well, you've got to put a space in. You're what? Propagating exceptions. Now this came out of the work of doing multi-threading. I've got a thread that generates an exception, and my parent thread needs to know, well, I've got to have some way of passing the exception across. Otherwise, all I know is it failed. Gee, thanks.
That's all you deserve to know.
All you deserve to know, yeah. Just abort the process you've done. Yep.
So the parent thread is doing something completely different in an unrelated function, and it gets an exception from a child thread.
It won't get an exception. What it is, when it does something to query the status of the thread, at that point it will be delivered with the exception. Yeah, it's not an asynchronous exception. Yeah, so I should have made that clear. So you do something like you join to your target thread, and you get an exception at that point, the one that was in the child. But rather than making it again happen by magic, they said, well, we'll actually do this stuff here, so that you can actually query what the current exception is, and you get back unspecified. What that means in standardised is don't even ask. It's probably compiler magic, and it won't be the same on the next platform you use. So don't make any assumptions about it. What it will actually say in your header file will be something else, but don't rely on it. However, you can use it, exception pointer current exception, and that will either return a value if I've got a current exception, or something that you can test against null, against 0, if there is no exception, which is also kind of nice actually, because there's no way of doing that currently in C++. If you try doing throw semicolon, what might happen? One of two things. Either it throws the existing exception, or terminate gets called because there isn't one. And how do you tell which it is? Well, you try it and find out. Not good. This way gives you a safe way of actually querying it. And then you can rethrow the exception later on. And of course, that object, you can actually copy it and pass it around. So that will actually be useful for more than just the original purpose, which is quite nice. Default and deleted methods. You've inherited something and you actually want to get rid of some of the methods. You've got the default methods. One of the classic interview questions is how many methods does a class have if you don't write any? And it's quite a few actually. You know, you kind of, yeah, probably 27 by now, the new version. A lot. You know, copy constructors and assignment operators and deletes and array delete and all sorts of stuff. And the problem is that the standard is quite clear. If you actually write one of those, that's different from the compiler-generated default. But now you can say, I want the default, please. And here's an example out of the atomics paper where atomic bool has a constructor from a bool, and it also wants a default constructor. So just say equals default. Without that line, you wouldn't have a default constructor. So that's quite cool. And similarly, you can say, I don't want that one, equals delete. I can see people using that quite a lot. The current trick is either don't bother, or do private around the copy constructor and assignment operation and hope you got the signature right, or use boost non-copyable, which kind of works, but it's a bit of a wart. Null pointer. So you can just have something that is a null pointer. Attributes, ways of marking code, marking variables, marking things with attributes. It's, again, open-ended. There are a number of things people come up with that might be useful here. Perhaps thread. Put this variable in thread local storage. The example here, no return, so that some sort of syntax parser can say, okay, you're not going to come back from that, so I don't need to worry about any code after that. Lots of possible uses for it. Little one, local classes as template arguments. This code currently doesn't work because you can't instantiate that against a locally defined class. So you have to break scope and put that outside the method. It's a small change, but quite nice. That used to work with VC 5, so it is implementable. Lots of library components, which there isn't time for. Again, if you want to use library components, that is a book that does cover them quite well. And they have been out there. A lot of them are derived from Boost. In fact, most of them are derived from Boost, and got quite a good track record. One of the bits that we had to work on was what I've described, eating our own dog food, which was, okay, so we've got all these nice new features in the language. Which of them makes sense to put into the library? The answer is, well, all of them, of course. And that's quite a difficult piece of work, and it's taken a lot of effort and is still ongoing. And there'll be more to come on the library side in TR2, which can be issued asynchronously to a certain extent from the core language, as long as it doesn't rely on any changed language features. Okay, there's quite a lot more in the presentation, which I'm not going to cover now. The presentation itself will be up on the website. The main thing to say now is, well, when's it going to be ready then? Okay, who wants it? Yeah, we all do. Well, the good news is that some of the new features are available in various builds of G++. There's quite a lot of stress that things shouldn't be put in the standard without being implemented, if at all possible. So there is an implementation out there. Not all the things kind of necessarily being put together yet. I don't know. Have they got a concept build with everything else? Anyone know? There's a concept GCC, which does all the concept stuff, and then there's a GCC branch with all the other goodies in, and there's a bit of work to kind of merge the two together. Microsoft have added a few of the features into their latest version of the compiler. EDG, Edison Design Group, have put a lot of the features into their back end, and it's up to the front end vendor how many of them they've enabled. And David, when I spoke to him, wasn't entirely sure, but things like the Intel compiler is based on the EDG backend and does have some of the support for the new features. And then after that, well, we have to wait, really, and see how long it takes for mainstream compilers to come out. The standard itself, we're hoping will still be C++ OX, but it's hex. No. In theory, it should be completed, final wording sometime around June this year, and then it takes a while for the process to go through before everyone's had a chance, all the national bodies have a chance to comment, and then it's not have to have the comments included in again and go round again for a set of voting, and it might just squeeze in before the end of 2009. But it's basically complete at this point. No new items are going to be included. Okay, well that's it on C++ OX. Any questions we can probably discuss later on in the pub, unless there's something that someone wants to say now that won't wait.
Thank you.
Thank you.